For this project, I will design, calibrate, integrate, and test a LiDAR sensor in order to map a target of my choice on campus. By using computer vision, software, and different data acquisition and processing techniques with Python, MATLAB, and MeshLab, I will create a 3D point cloud and mesh of my target. This project allows me to experience firsthand how remote sensing can be utilized, such as by mapping the campus or by being able to recognize a parking meter with computer vision software when driving a car autonomously in order to know where to park. This project has also helped me just be able to understand LiDAR better and how remote sensing works exactly. The target that I chose for this project is a parking meter in between Moat Lane Garage and Prince Frederick Hall. I chose this project because it is close to where I live, and I was interested to see how features such as the shiny black material and features such as buttons and slots would show up in the point cloud. Remote sensing is a technology of obtaining information about a target without having to come in direct contact with it, and this range data can be obtained by knowing the time of when the signal is sent and received and multiplying that by a light or sound constant and dividing it by 2, and this gives the range data. So there are two types of remote sensing, passive and active. Passive has no self-generated radiation, and active has self-generated radiation in the sensing process. This project will use active remote sensing because of the use of a laser, which is a self-generated radiation. Speaking of the laser, LiDAR stands for light detection and ranging, and this uses light in the form of a pulsed laser to get range measurements. This project also deals with computer vision, and that is a technology that a computer is able to take images or data and interpret that data and say, this is a human versus a stop sign, basically programming a machine to do what the human eye could. For the LiDAR sensor design, the line laser is a transmitter and the camera is a receiver. The Raspberry Pi will process the data, and the iPhone acts as an accelerometer to tell the angle. All of these are mounted onto a 3D printed mount, and as you can see, the camera and line laser are in line with each other so that the camera can get the line laser data directly and won't be misaligned, but they are also 12 inches apart, which is set in the calibration curve. All of this is also mounted onto a tripod so that the mount can be angled in the correct position. Here is the calibration data for a single beam laser and the line laser. The blue line represents the theoretical data and the red line represents the taken data. These calibrations were done for a separation distance of 12 inches, and within the Python script, the RO and RPC values were changed in order to get the calibration data to line up as closely as possible to the theoretical line.
Here's my data acquisition setup. Here's the Raspberry Pi, the mount, the laser, and the tripod, and they're powered through my laptop, and here is the target. One notable thing about this target is that it is reflective, so you can see the reflection of the laser circle on the back of it. Another thing here is that there's a street lamp right there, and it's shining down right on top of it, so this side is a little bit dark, so the color picker will have to be able to pick out the laser. But other than that, this side of the parking meter is just very flat, pretty simple. So here I will run the code. We'll do data collection. This angle, I will adjust it. So now the angle should be 348. And there we go. There's the image in the folder. After taking the data for the right, left, and back sides of the parking meter after taking the front side last week, I transferred all of the files to my laptop from the Raspberry Pi and used the data generation Python file to convert the points into a text file. So I applied an HSV for each side of the parking meter and adjusted the RO and RPC values as needed. So going into the MATLAB portion, I use the 3D cloud file for each of the sides to filter the data and plot it into a 3D point cloud. So as you can see, this is the filtering, basically saying if it's in a certain Y range or an X range, then it would be considered to be noise, so all those points are just set to 0. So plotting the right side as an example, here is the unfiltered cloud. As you can see, there's a lot of noise, and here is the filtered one. It's a bit more clean, and you can kind of see the rectangular shape of the parking meter. So then combining them all into one point cloud, here I have all the data being imported, and then cleaning each one individually and filtering out all of the noise. And then applying a few transformation matrices by rotating the left side by -90 degrees, the right side by 90 degrees, and the back side by 180 degrees, and keeping the front side the same. These are all rotated and also transformed, like in displacement here, just by looking and kind of guessing and checking. So, and then plotting the data down here, so we'll run that code. And here you can see it's not transformed, so all the points are kind of just lying on top of each other and you can't really make anything out of it. And here's the transformed data. It's a bit better. You can see that here's the front, there's the back, and the sides. So you can kind of see, of course there are some big errors, I guess, in my point cloud, in that this is bending outward and it's a little bit warped. So still need to make some adjustments to get it to be more accurate. But yeah, here it is, and here's the untransformed one. You can see there's kind of like sheets lying across each other. In order to create the 3D mesh, I first fixed my point cloud from the previous homework. So my point cloud, some of the sides had bulges in them, so in order to fix that, in the Python code where the Y output is being written, I subtracted out these values, and this fixed angle and bulge constant I got from looking at the original point clouds and kind of guessing and checking with different points on the point cloud to see what angle and what constant I would need in order to make it line up with the Y value that was at the 0 angle. Here is the new point cloud. As you can see, all the sides are a lot straighter. You can tell it's more of like a rectangular box now.
Looking at a direct comparison between the right side picture and 3D point cloud, you can see how where the blue and green stickers are of the parking meter, the point cloud is a little bit more sparse because the color picker HSV values were set for the black area of the parking meter. So that is one area where the point cloud is a little bit lacking. Overall, I will say that the point cloud does pretty accurately represent the actual parking meter. As you can see, after straightening it out and after filtering it, the end result is pretty rectangular and pretty straight. And you can also notice, if you look closely, that the front of the parking meter also has a rectangular cutout in the bottom half where the screen actually is, so it is pretty accurate.
In order to output this into a text file, I took each of the point clouds and put them into matrices and then combined those into one big matrix. And then I went through the total matrix line by line and printed each line, each XYZ coordinate basically, into this file that I named cloud_total.
So now in MeshLab, we have imported the mesh, as you can see here. And first we need to create the normals, and we will set this value to 1, and then we can create the Poisson surface reconstruction. We'll use a value of 15 here, and that will give us this mesh. As you can see, there's a lot of extra surface here, so we can take that away by using this, by using the surface trim tool. So after trimming off the surface, we end up with this mesh. And it's definitely not perfect because of the sparse areas in the point cloud. There are some areas such as here and here that are a lot more sparse on the right and left side. It is pretty rectangular, I would say, after trimming it.